So in this video we're going to define and then calculate a torque. So torque, the definition of torque is you let P be a point of rotation. So in my picture this is going to be the point of rotation right here. P be a point of rotation. So we're going to rotate something around a point. Let P be the point of rotation. Let Q be the point. So that would be right here. This will be Q. This will be P. Let Q be the point at which a force F is applied. And then R is going to be the direction vector from P to Q. So we're going to let R equal the direction vector PQ. And then F is a point force that's applied at Q. And this thing's going to be something that is rotatable. So the torque, tau, is defined to be the cross product of the position vector with the force vector. So this is just the definition of how definition of torque. Torque is important, so when you're doing things like tightening the bolts on your wheels for your car, they usually have torque specs. I think it's like around 100 pounds typically. Over tightening or under tightening both can lead to mechanical failure. So torque is something that's important in engineering. And the other thing we want to remember is that the cross product from the geometric cross product properties, the cross product is perpendicular to the two vectors. So tau is going to be perpendicular to both R and F. So tau is either going to point out of the screen at us perpendicular to the vectors R and F, or into the screen perpendicular to R and F. And the direction depends based on what's called the right-hand rule in physics. It's based on the direction of rotation. When you take physics, which you'll most likely do if you're taking this particular class, you'll go over the right-hand rule. So an example of how to calculate a torque. So here I went online last night and I found a picture of a pipe wrench they were trying to sell. And then I made up a story to go with the picture of the pipe wrench. So my story is a force of 50 pounds is applied straight down to a pipe wrench when the pipe wrench makes a 30-degree angle with the horizontal. And that's kind of an ambiguous statement if you don't have a picture to go with it, because 30 degrees with respect to the horizontal could mean 30 degrees up or 30 degrees down, depending on the situation. So a 30-degree angle with the horizontal, and the force is applied 16 inches from the center of the bolt that's being tightened. Find the magnitude of the resulting torque. So the idea here is we want to establish, first and foremost, because we need vectors, we need a position vector and a force vector, we need to establish a coordinate system in which we can construct those vectors. And I'm going to do it two ways. I'm going to do it the way first that I think is less common, but it works out well for this particular application. And then I'm going to establish a coordinate system based on how I think you would usually do it for this type of a problem. So the idea is we're tightening a bolt, and they're telling us that we're tightening the bolt, which means we're actually rotating the bolt righty-tighty, probably in the clockwise direction. And the center of that is going to be the point of rotation. So here's my point of rotation. And so typically you're going to take the point of rotation and make that the origin of your coordinate system. So I'm going to establish a coordinate system here at the point of rotation, hopefully. And so one way I could do is establish it in the the typical vertical horizontal position. So point of rotation, and this could either be a YX coordinate system, and remember torque is defined as a cross product, and cross products require three-dimensional vectors. So that means I need a Z. If I make this Y and X, I need a Z axis pointing out of the screen. So this would tell me everything in my picture is going to be in the YX plane. So my Z components would be 0. I could decide to make this the Z axis and the Y axis, in which case everything is in the ZX plane and the Y components would be 0. I could decide to make this the Y axis and this the X axis. Axis designations are arbitrary. You get to kind of decide how you want to orient axes. So then everything would be happening in the ZY plane, and my X coordinates would all be 0. I'm going to choose to make this the YX plane, with the z-axis coming out of the screen at me, the positive z. So my z components for my vectors will all be zeros. Once I've established my coordinate system, I need to describe my vectors in the coordinate system. So I know I have a distance vector, r, coming out here, and I've been told at a point 16 inches down that I'm applying a force vector of 50 pounds straight down. And what I need to do is represent these vectors, the distance vector, in my coordinate system. So if I'm making a 30-degree angle from the horizontal, based on how I've constructed my coordinate system, this is really going to be a negative 30-degree angle because I'm rotating from the positive x-axis in the clockwise direction. So a unit vector, I can get a unit vector in this direction from trigonometry. So if I just start to think about building the position vector r, I can get a unit vector by taking from trigonometry the cosine of negative 30 degrees, comma, the sine of negative 30 degrees, comma, and then the z component 0. And these live on the unit circle in the y-x plane, so the cosine squared plus the sine squared is equal to 1. I know this is a vector of length 1, and then I just take my scalar 16 and I multiply 16 times that unit vector to get the position vector r. And then I can simplify a little bit because from trigonometry I know that the cosine of negative 30 degrees is the square root of 3 over 2. And the sine of negative 30 degrees is negative 1/2. And I know that 0 is 0. Notice I could actually, if I wanted to, factor a 1/2 out of this if I felt like I wanted to. I'm not going to leave it alone, but I could, and there'd be nothing wrong with doing that. Now I need my force vector. My force vector is going to be really easy because it's working straight downwards. It's working parallel to the y-axis. So a unit vector on the y-axis that points down would be a vector 0, no x component, negative 1, no z component. There's a unit vector pointing down parallel to the y-axis. So I would take my size of my force and multiply it by that unit vector 0, negative 1, 0. So now I have my two vectors, and then I want to remember the torque calculation. Torque, tau, is equal to r cross f. So if I calculate the torque to find the magnitude of the torque, I would just find the length of the vector r cross f. So if we do this cross product, what we recognize is we're taking the cross product of 16 times root 3 over 2, negative 1/2, and 0. We're crossing that with the vector 50 times 0, negative 1, 0. And remember, from cross product, the algebraic properties of cross products, if we have scalars, we can factor those out front of the cross product calculation. So I can do 50 times 16 times the cross product of the two vectors. So keeping these scalars factored off, because we're going to do a cross product calculation, is a nice thing to do. So I'm going to have I, j, k, and then it's going to be the position vector. So I'm going to be plugging in my root 3 over 2, my 1/2, and my 0. And then I do my force vector, so I'm going to get 0, negative 1, 0. And then before I even do the calculation, because I know the cross product has to be perpendicular to r and f are in the xy plane. To be perpendicular to r and f, I'm going to have no x and y components, and everything will be in the z direction. And so if we calculate this cross product, here's my 50 times 16. If we think about calculating the I component, we'll get a 0. Cross row 1, column 1, we have a little 2 by 2 determinant we have to calculate that's left. It's going to be 1/2 times 0 plus 0 times negative 1. There's going to be no x component. And then the y component would be the opposite of j. We'd cross row 1, column 2, but we'll get what's left is going to be this times 0 minus 0 times 0, 0. There's going to be no y component. Only thing that we're going to get is we're going to get 0, 0. The only thing we're going to get is the z component, and that's because we have to be perpendicular to the x and y axes because all the action is in the xy plane. So we cross row 1, column 3, we're going to get root 3 over 2 times the negative 1 minus the 1/2 times 0 is going to be a negative root 3 over 2. And then if I factor this off, I can factor the negative root 3 over 2 out. And if I do that, I get 50 times a half of 16 would be 8. And I'd have a negative, and this would be root 3. And inside of here, I leave the negative on the inside. In fact, this would be 0, 0, negative 1. So if I do that factorization, I get 50, the scalar 50 times 8 times the square root of 3 times the vector 0, 0, negative 1. So notice this, the magnitude of the torque is actually just going to be the scalar. 50 times 8 is 400. We get 400 square root of 3. And this is going to be inches. So I've got, based on how I did it, I have inch and pounds. I have inch pounds. Usually you do foot pounds, but I left it in inches, and that makes me happy. If I needed the calculation in foot pounds, instead of 16, we would do 16 over 12 to make this an inch measurement, right? We could, if we wanted foot pounds, just say it's over 12, it's over 12, it's over 12. So we could divide this result by 12 to get a measurement in foot pounds. The key is that this vector, if I factor the root 3 over 2 out and just leave the negative 1 inside, this vector has length 1. So this, and if it has length 1, that means the size of the torque is just the scalar. That's the key. I get the scalar as the size of the torque by factoring it out. If I were to calculate the size of this, I would just get 1. So another way to do it, and probably the more common way to do it, you still need to establish a coordinate system, so we go to the point of rotation. But it's probably more common to put either an x or a y axis along the position vector. So you establish an axis here, so that means if I decide this is an x-axis, my y-axis would need to be perpendicular to that. So it's really common to establish the origin at the point of rotation, and then put the x-axis parallel to the position vector, and then draw the force vector into the picture. So I got the force vector right here. He's 50 pounds. So you can think about what's going on if you do this. The position vector then becomes easy to describe. The position vector is going to be the vector, hey, it's 16 inches to here, but I'm along the x-axis now, so it's really going to be 16 times the unit vector 1, 0, 0, just 16 times the vector I, 16i. We could represent that. So then the position vector winds up with the simple representation, and then the force vector, we need to come up with that. So the force vector is working straight down. Remember, vectors don't care where you draw them in the plane. So the force vector, if I draw it here and think about how to get him, if I dash the horizontal in, I know that my axis, because it's parallel to the position vector, is making a 30-degree angle right here, and then I can use that to figure out where is my torque vector living in this coordinate system. I know this angle here is a 90-degree angle. So what is the angle right here? And it's going to have to be a 60-degree angle, because 60 plus 30 adds up to the 90. So I know that this angle here, relative to my x-axis I've established, is going to be a negative 60-degree angle. And then I can use that to come up with my force vector. So my force vector in this coordinate system is going to look like the 50 pounds times a unit vector, but the unit vector is going to be the cosine of negative 60 degrees sine negative 60 degrees, comma, nothing going on in the z coordinate system. So when I do this, I get 50 times The cosine of negative 60 degrees is going to be a positive 1/2. The sine of negative 60 degrees is going to be negative root 3 over 2 and a 0 in this position. So then when I go ahead and do my torque calculation, torque, tau equals, it's going to be R cross F, which is just going to be the scalars, 50 times 16. Factor those scalars off front, and then it's going to be 1, 0, 0 crossed with our vector 1/2 negative root 3 over 2, 0. So we're going to get 50 times 16 times the determinant I, j, k, and then my position vector is going to be 1, 0, 0, and I'm going to get 1/2 negative root 3 over 2, 0. And again, I expect the x and the y components of the torque vector to be 0 because the torque vector has to be perpendicular to the xy plane. So if you cross row 1, column 1 to get the I component, you're going to get 0 times 0 minus 0 times negative root 3 is 0. Cross row 1, column 2 to get the minus j component, we're going to get 1 times 0 minus 0 times 1/2. And then, so we're going to wind up with a vector here. The torque vector is going to be 50 times 16 times, and then we need to do our calculation for the k component. We get 0, 0, and now something in the k, cross row 1, column 3, we get 1 times negative root 3 over 2 minus 0 times 1/2 is just negative root 3 over 2. And then from here you play the same game that we did the last time. Factor out a root 3 over 2, which will halve the 16 to an 8 and give us a square root of 3 times the vector 0, 0, negative 1. And because, like before, this is a unit vector, the positive scalar out here is going to be the torque. So the magnitude of the torque, tau, is just going to be the 50 times 8 is 400 times the square root of 3. And again, I calculated this in inch-pounds. We would need to divide this result by 12 to get it in the standard foot-pounds, because all we would be doing is going through everywhere in the calculation and dividing that 16 by a 12 if we wanted to convert it into a foot-pounds calculation. The point here is it's frequently going to be, especially if the force is applied at funky angles. If you apply the force at funky angles other than just straight down or straight up, it's going to turn out that establishing a coordinate system here where the x-axis or the y-axis runs parallel to the position vector is going to allow you to more easily come up with the force vectors that you need when you draw your diagram out.